Good morning, everybody. Going to give people about a minute to start or join, and then I will start. Quick little recap of just chapter 12, the kind of stuff that will be on the celebration or on the quiz. Okay, let me get this straight. Important to get the hat right. Okay, so while people are joining, I want to just talk a little bit about chapter 12. So let me just say that the homework for chapter 12 is probably one of the most challenging homeworks, and I didn't cover everything in enough detail to do a few of the problems. And I realize also that I skipped the parallel axis theorem. But the quiz, like the other quizzes, will be much more straightforward. Keep in mind also that the homework solutions, just like before, are still posted for the entire semester. So you can sort of use those homework solutions as a little guide to help you out. But what I want to do is just be specific about, in terms of chapter 12, the kinds of material that are going to be on it. So first off, first thing I did with chapter 12 was just talk about the cross product. Whoops, how did that just happen? So in terms of things you should definitely know for the chapter 12 quiz is cross product. In fact, I'll tell you without a doubt, you will have a cross product question. So angular position, velocity, and acceleration, all of this stuff was sort of from chapter 4 that I didn't cover before when I was dealing with chapter 4. Things important are rotational kinematics. So remember, for every equation that we had for linear acceleration, there's also a corresponding equation for angular. So things like omega equals omega naught plus alpha t, theta equals theta naught plus naught t plus 1/2 alpha tc. Hold on one second, let me just mute everybody. Why can't I do that? Yeah, manage participants. Mute all. Okay. Yes. So other things from chapter 4 that are important are the relationship between linear quantities and angular quantities. So keep in mind that our tangential speed is related to our angular speed by v equals r omega, and our tangential acceleration was related to our angular acceleration, a equals r alpha. Went through center of mass, which is basically the average position of the mass of an object. You should know how to calculate the center of mass if I were to give you just a collection of point particles of different masses at different locations. Talked about rotational energy. So keep in mind, if an object is just rotating, it has a form of rotational energy called rotational kinetic energy, and it's 1/2 I omega squared. I is called the moment of inertia, and there's a simple equation if it's just a collection of masses. If it's something like a disk or a solid sphere or a cylinder or a spherical shell, there's equations in chapter 12 that you can use just to get the moment of inertia. And then torque, that's the other big thing here, is looking at Newton's second law for rotations, which says the sum of the torques equals I alpha. And remember, torque, the magnitude of the torque is R F sine of theta. And keep in mind, when you're looking at that angle, you always draw R and F tail to tail, and the angle theta is the angle between R and F. Don't worry about angular momentum. Don't worry about the vector description of rotational motion. So things to focus on for chapter 12 quiz is, what is the cross product? How do you do it? Looking at the definitions of the circular quantities. So what does theta mean? What is omega? What is alpha? How do you relate linear quantities to angular quantities? So V equals R omega, A equals R alpha. What is the center of mass? And then looking at rotations. How is torque defined? and looking at Newton's second law, the sum of the torques equals I alpha. And the very last thing we were looking at is kinetic energy of rolling. And if something is rolling, it has two forms of kinetic energy. It's got a 1/2 mv squared, where this is the speed of the center of mass, and it's also rotating. So I have a 1/2 I omega squared. And the way you always end up dealing with this 1/2 I omega squared term is you replace omega with V over R, and you replace I with some number times mr squared. So if it's a cylinder, it's 1/2 mr squared. If it's a solid sphere, we've got 2/5 mr squared. If it's a spherical shell, 2/3 mr squared. So let me just stop that. Before moving on to chapter 15, are there any just general questions I can answer about chapter 12? Not specific homework questions, but just things that you're not sure whether or not you need to know in detail or things like that.
Hey, Joe, could you repeat the last thing you said in regards to the number changing in regards to the shape of the object?
Yeah.
For the rotation?
Let me share this again. Share screen. So let's just say like I had let me just pull up a different thing. So let's say I had a rolling sphere, and I wanted to know something about the kinetic energy of the rolling sphere. So if I got a sphere which is rolling, moving through space with some speed v. And again, that's the speed of the center of mass. So one thing I kind of mentioned that's very interesting about a rolling object is if I have an object which is rolling without slipping, the center of mass is moving forward at some speed. The speed at the very bottom where the wheel is touching is actually instantaneously 0 for a split second. And the speed at the top of the wheel is actually twice the speed of the center of mass. But anyway, going through kinetic energy of rolling, we've got two terms. You've got a 1/2 mv squared term, and that's just because the center of mass is moving through space. So if instead of rolling, this ball was just sliding at some speed, it would only have this translational kinetic energy 1/2 mv squared. But if it's also rolling, then you have this 1/2 I omega squared term. So let's consider this a solid sphere. So for a solid sphere, I is equal to 2/5 mr squared. So what I would do in terms of this kinetic energy term is I would replace I, so one, I still have this 1/2 mv squared term. I'd replace I with the appropriate equation. So if we're talking about a solid sphere, it's 2/5 mr squared. If we were talking about a cylinder, it'd be 1/2 mr squared. We're talking about a spherical shell, so just kind of like an empty ball with all the masses on the outside, it'd be 2/3 mr squared. And then I replace omega with v divided by r. So this little piece here becomes 1/5 mv squared. So that's the rotational kinetic energy piece. I still have this 1/2 mv squared. This is the translational kinetic energy. So the total kinetic energy of rolling for a solid sphere, which is rolling at some speed v, would be 1/2 plus 1/5, which is 7/10 mv squared. So this is pretty much anytime you've got an object which is rolling, or even just like an axle which is spinning, you always replace I with whatever the function appropriate for that type of object is. And then you always replace omega with v over r. All right, let me just stop that share. Let's just see what the chat was. It would be 2 at the top of the rolling wheel, correct? Yes. Oh yeah, I don't know if I wrote 2 on that, but it's, oh, sorry. So yeah, back to this share real quick. Screen share. Yeah, this speed at the very top, this would be twice the speed of the center of mass. And I think I showed you, if you see a picture of a wheel where you can take a picture of it as it's rolling by, which you would see is the top of the spokes are blurry, and you can clearly see the spokes at the bottom, because at the bottom, that point touching is actually momentarily at rest for a split second. Okay, let me open it up to homework. There's a problem asking about objects rotating about a shifted axis. So One thing I didn't cover, and I can just touch on it really quickly, is what's called the parallel axis theorem. And I do realize that you had a homework problem or two that I'll touch on it. So let me just share that screen again and let you know what it is. So all of these equations that we've had so far, like for a cylinder, or let's just say for the solid sphere, these moments of inertia are actually the moments of inertia about the center of mass. If I wanted to know what is the moment of inertia about an axis parallel to the center of mass. So like our classic example is the moment of inertia about a rod passing through the center is, what is it, 1/12 ml squared. But if I wanted to know what is the moment of inertia about an axis passing through the end, not through the center of mass, then this parallel axis theorem says that the moment of inertia about an axis passing through the center of mass, I'm sorry, about an axis parallel to an axis passing through the center of mass is the moment of inertia about an axis through the center of mass plus md squared, where this d is the distance from the center of mass. So for example, if I wanted to know what is the moment of inertia about an axis passing through the end of a rod, well, I know the axis passing through the center of mass, the moment of inertia is 1/12 ml squared. Well, an axis passing through the end is located a distance L/2 away from the center of mass. So if I wanted to know what is the moment of inertia passing through an axis at the end, it would be the moment of inertia through the center of mass, which is 1/12 ml squared, plus m times d squared, where d is the distance from the center of mass. And then if you add these two together, what you end up getting is 1/3 ml squared. So it's just sort of a simple formula. I'm not going to focus on it for the quiz, but I'm just going to throw that out there because I did not cover that during lecture, I realized. Okay. So what I want to do is, if there's no other questions, I want to just start on chapter 15, simple harmonic motion. But again, 30 seconds if anybody has any questions about chapter 12 and things that might be on the quiz for Saturday, or for Friday, tomorrow.
Can you put the screen with all the equations back on for a bit?
This one that I just did?
The first one.
More example problems. This one?
Yeah.
Okay.
Thanks.
You are welcome. Okay, so I mentioned this before. We've got 4 more lectures, basically. I've got 3 chapters to cover. I'm only covering bits and pieces of each chapter that I know you're going to need for Physics 4B and Physics 4C. One of those is simple harmonic motion, and that's chapter 15. So what I do is spend today introducing and talking about simple harmonic motion. So let me open up chapters 15 through 17. Go up here. Sorry about that. Okay, and let's share the screen. Okay, so now we are starting officially chapter 15. It's all about oscillations. And this chapter, we're really dealing with what's called simple harmonic motion, which we write as SHM. And any system, so let me preface this by saying that we are usually looking at a mass connected to a spring when analyzing simple harmonic motion. And it's not because springs are so important, it's because there's many physical systems that can be modeled like a spring. And if you remember, the big thing about a spring is the force a spring exerts is equal to negative K times delta X. So one you'll see in some of these notes, X, I think last year I was just tired of writing delta X, so I just started writing X. But delta X is how far the spring is stretched or compressed from its equilibrium position. And then K, remember, was the spring constant. The big thing about simple harmonic motion is it's very periodic, and the position, velocity, and acceleration I can describe by either using a sine or cosine function. And what really distinguishes a system that obeys simple harmonic motion are two things. And these are sort of the hallmarks of simple harmonic motion. It's this: either the force goes like negative some constant times the displacement, or the acceleration is negative some constant times the displacement. So negative some, well, let me just put it this way. The acceleration, where's my eraser, is proportional to negative the displacement. Meaning the farther I get from the equilibrium position, the bigger the force is pushing me back towards equilibrium. Or the farther I get away from the equilibrium position, the bigger the acceleration is in the opposite direction. So we call these kind of forces just anything that obeys this sort of where the force is negative a constant times the displacement, a restoring force. And I want to just show you just one thing over here in these applets. I've got some applets that I'm going to show you in a second. Here's the links to them if you wanted to access them yourselves. So first, we do a little new share. So here, a couple different systems that obey Hooke's law or show sort of a simple harmonic motion kind of behavior. So one, we'll see this towards the end, but a pendulum swinging back and forth, I can use sine, cosine function to describe position, velocity, and acceleration. Up at the top, if you were to hit a drum and look at the membrane of the drum will oscillate up and down in simple harmonic motion. Or even a speaker, as this thing is moving up and down, it is oscillating in a very periodic way, obeying simple harmonic motion. And one of the things I'm going to go through in a second, which is really cool, is there is a relationship between simple harmonic motion and circular motion. And let me just show you this here. So as this object is, let me just play this real quick, moving around in a circular path. Can I adjust this? Let me reset this for a second. What you'll see is if I look at the y component of this displacement vector as it's moving through space, it is going to trace out, in this case, a cosine curve. So one of the really cool things about simple harmonic motion is it's directly related to uniform circular motion. So if I have an object moving in a circular path at some angular speed omega, and I look at the y component of this as it's moving, that will trace out the position of an object, let's say oscillating up and down in simple harmonic motion. I'll show you this in a second once we do these equations, but let's do this again. Displacement. I pull this thing, reset, pull this down and let it go. If I imagine an object moving in uniform circular path at a constant speed, and I just look at the y component of this, the y component of this displacement vector as this moves is going to trace out the path of this thing as it oscillates up and down. So continuing forward, you know, like right here, I'm at basically my equilibrium position. And as this thing continues, at every point, if I look at the y component, that's tracing out the position of this mass as it oscillates up and down in what's called simple harmonic motion. Now, one really cool thing, if I have an object which is moving in a circular path and I want to plot the velocity vector, remember velocity is always tangent to the path. So rather than looking at the displacement vector, velocity remember, is always tangent to the path. And if I draw the velocity vector as this thing moves in uniform circular motion, and I look at the y component of that vector, that'll give me the velocity of this mass as it's oscillating up and down. So for example, right here, this is when it's moving the fastest, pointing down. And if I look at the y component of this vector, it's got the largest negative value. Then as I continue forth, at the lowest point, it's momentarily at rest for a split second. If I look at the y component of this or velocity vector, it's 0. Then as it keeps moving, as it's crossing the equilibrium position on the way up, that's when it has the greatest velocity pointing up. And again, if I look at the y component of this velocity vector, it has its greatest value. And then again, as it continues forth, right here, the y component is 0. At the very highest point, it's at rest for a split second. It's really pretty cool. Now, one more quick question for you. If I were to draw the velocity, or not the velocity, the acceleration vector for something moving in uniform circular motion, how does the acceleration point? Well, it always points towards the center of the circular path. So if instead of drawing this velocity vector, come on, acceleration, I look at the acceleration. And again, if I look at the y component of this acceleration vector, which is pointing towards the center, that'll give me the acceleration of the block. So when the block is stretched the most, remember F equals negative kx, when the force is biggest, that's when the acceleration is biggest. So in this case, my acceleration has its greatest value pointing up. When is the acceleration going to be 0? When the spring is not stretched or compressed, when it's in its equilibrium position. So as this thing continues, let's go back up. Here's it's crossing the equilibrium position. My acceleration vector for something moving in circular motion always points towards the center of the circular path. If I look at this y component, it is 0 at this point. The acceleration of this mass is 0. And if I look at all three at the same time, that's a little confusing, but you could sort of step through it. These are called phasors. I don't know if you've had this yet in any of your math classes, but a phasor is just a projection of a vector onto an axis. So like right now, this object is moving upwards, the displacement is up, the velocity is up, but it's slowing down, so the acceleration points straight down. The values of those I could get by looking at the projection of this displacement vector, this velocity vector, and this acceleration vector in the negative y direction, or in the y direction. Okay, that was just a little overview. Let me just go back to the math of simple harmonic motion. Okay, quick chat. Let's chat. So the diameter of the circle is equal to delta y of the object on the spring. So you could relate the diameter of the circle to certain physical characteristics of the system. For a spring mass system, well, I'll touch on that at the end, but the answer is yes, you can relate them. And what I'm going to show you, just as a little preview, the general solution to a object oscillating back and forth in simple harmonic motion is A, which is the amplitude, times cosine omega t plus some phase angle. That omega is the same thing we were using for circular motion. It is angular speed in radians per second. Well, for simple harmonic motion, we call that, it's related to the angular frequency, but it's also in radians per second. And if I describe simple harmonic motion using this equation, this omega here would be the same as the angular speed that this thing moving in circular motion was moving at. Okay, so going back to this. So we're going to consider our simple system to be a mass connected to a spring. And again, the reason we're doing this is because it's a simple physical system that you can look at in the lab. Everybody's played with springs before, but it's not that springs are so unbelievably important. It's because there's many systems that behave like where the force is negative some constant times the displacement. As I get farther from the equilibrium position, the force pushing me back towards equilibrium gets bigger and bigger and bigger. So just as a quick little review, and again, this should be delta x, delta x, delta x. Keep in mind, x equals 0 is sort of my equilibrium position where the spring is not stretched or compressed. When the spring is stretched, we generally are considering the displacement delta x to be greater than 0. When the spring is compressed, we're considering delta x to be less than 0. Just a couple sort of vocabulary terms. A is the amplitude, and it's the greatest distance from the equilibrium position. So if I pull a spring 10 centimeters and release it from rest, it's going to oscillate back and forth, constantly moving 10 centimeters away from the equilibrium position on either side. A cycle is considered one complete back and forth motion. So if so let's say here's my equilibrium position. Here. If I pull a mass some distance delta x and release it from rest, one complete cycle is this mass moving, and this would be my A, this mass moving from x equals A to x equals negative A, and then back to x equals A. So one cycle is one complete back and forth motion. So I pull something distance A, one cycle would be for it to go from one extreme to the other, and then back to its original starting point. So that would be one cycle. Period, just like we've seen before, period is just a time, and it's how long it takes for one complete cycle. And then frequency, again, just like we've had before, is the number of oscillations per second. So if something is oscillating back and forth 10 times a second, the frequency would be 10 hertz. The time for one cycle would be 1/10 of a second. So frequency and period are inversely related. Frequency is 1 over period. Period is 1 over frequency. Okay. Let me teach you all of differential equations in 2 minutes. Here's how all of differential equations work. You have an equation, you guess at the answer, you make it work. I've saved you an entire semester's worth of work. This is differential equations. You have an equation, it has sort of a general solution, and then you make that general solution work for whatever system you're talking about. So let's look at our simple system, and that is a mass on a frictionless surface connected to a spring oscillating back and forth. And if I were to draw the forces acting on this mass, I just have the normal force, I've got gravity mg, and I've got the force of the spring. And that's going to depend upon whether this is stretched or compressed. But if I only look at the sum of the forces in the x direction, there's only one. So if I apply Newton's second law, sum of the forces in the x direction equals max. The only force is the force that the spring is exerting. And let me just write this as x rather than delta x. So what I get is negative k, which is a spring constant, times x, which is how much the spring is stretched or compressed, equals max. Well, I can write acceleration as the second derivative of position with respect to time. So what I get is negative k times x equals m times the second derivative of x with respect to time. And then if I just solve for this second derivative, what I get is the second derivative of x with respect to time is negative k over m times x. This right here is a differential equation, and it's the differential equation for simple harmonic motion. So in essence, what I'm looking for is what kind of function, if I take two derivatives of it, returns the original function times some constant which is negative. And the answer you probably know is either sine or cosine. So if I take two derivatives of sine or two derivatives of cosine, I'm going to get sine or cosine back, but with a negative constant out in front. So differential equation. I have an equation, I guess at the answer, and then I make it work. So I know that the general solution to something where if I take two derivatives of it with respect to time gives me the original function back times a constant, sine or cosine. So here's what you do. you have a general solution, and then you sort of make that general solution work for the particular system that you have. So the general solution to the second derivative of x with respect to time being some constant, negative some constant, which in this case is k over m times x, is a cosine or sine function. We're going to choose cosine. So here's our general solution. My position as a function of time equals some amplitude times the cosine of omega t plus some phase angle. So A, like I said, is the amplitude. It's just my maximum displacement from the equilibrium position, and that's in meters. Omega is called the angular frequency. It's in radians per second, and it's related to the angular speed that an object moving in uniform circular motion would have. T is just the elapsed time, and then I'm going to talk about the phase angle, but this is important because if it wasn't there, so let's just do this real quick. If I had a phase angle, there was no phase angle. So my general solution was just my position as a function of time equals A times cosine of omega t. This is not a complete enough function to describe all the different possibilities, because the way this is set up, at t equals 0, I get my position is A times the cosine of 0, which is just A. So if I didn't have that phase angle and I had an equation for position as a function of time that was just A cosine omega t, then I would always have to have x equals A at t equals 0. And in fact, let me just share this again with you to show you. Simulator. Okay, let's reset this. So again, if I have, can I increase the mass of this? No. So as this thing is moving in circular motion, if I look at the projection of the y component of this, that's going to describe the position of a mass oscillating up and down in simple harmonic motion. Well, if you notice, let's reset this. If I'm starting off at, well, can I just do this x equals A? Can I rotate? Okay. So this would be me starting off at something where I'm at the amplitude at t equals 0. If, though, I wanted to start it at a different position, so let's just say that what would happen here? Hold on one second, technical difficulties. If I wanted this object to start here, oh, now it's not doing it, both. If I wanted this system to start here, I cannot describe that as just A times cosine omega t, because at t equals 0, cosine of 0 is 1, I would always have to be at x equals A. So going back to this, this phase constant is almost like our x naught, v naught when we're talking about uniform motion in one dimension. It describes the initial conditions. In essence, it describes my initial position and my initial velocity. I need that so that I can have the option of not always having to have x equals A when t equals 0. Okay, so here is my general solution to our differential equation for simple harmonic motion. What I want to do is just show you that if I ever have a function of position versus time, I can always differentiate that and get velocity versus time. And if I have a function of velocity versus time, I can always differentiate that and get acceleration versus time. So if I take a derivative of x with respect to t, and here is my function, A, which is the amplitude, cosine omega t plus phi naught. Derivative of cosine is negative sine, and I also have to differentiate what's on the inside. So taking derivative with respect to time, I pull out an omega. So my equation for velocity as a function of time is V is negative A omega sine omega t plus phi naught. And I get that just by taking the derivative of position versus time. Let me just quickly check on chat. Can you scroll up to the last page? Can you define phi again quickly? Okay, here's the last page. And phi naught is a phase, it's called the phase angle, but I'll do this in a little bit. It describes my initial positions at t equals 0 and my initial velocity at t equals 0. And the reason we need it is because if there wasn't a phase angle, so if my position versus time function was just a cosine omega t, then there is no flexibility there. At t equals 0, I'm going to get x equals a, which means if this was my function, I would always have to start at x equals a at t equals 0. Well, this phase angle, in a sense, gives me some flexibility. Now I can have my initial position not being x equals a. I can have my initial velocity not being 0. I'm going to show you how to calculate it, but the phase angle is determined by my initial position, my initial velocity. Okay, so taking one derivative of position versus time gives me my velocity. So my velocity versus time is negative a omega sine omega t plus phi naught. And this right here, we call my max speed, V max, right? Sine can only vary between 1 and -1, which means my velocity is constantly varying between V max and negative V max, where V max is a omega. And again, keep in mind the units. A is my amplitude. This is measured in meters. Omega, we call my angular frequency, and this is in radians per second. And when I multiply meters by radians per second, I still end up with units of meters per second. So now if I want the acceleration is just two derivatives of position with respect to time, or if I differentiate velocity with respect to time. Well, if I take derivative of sine, I get cosine. And again, I need to take the derivative of what's in the inside, so I pull out another factor of omega. So my acceleration versus time is negative a omega squared cosine omega t plus phi. And again, since cosine always varies between 1 and -1, my acceleration is going to vary between a omega squared and negative a omega squared. So my maximum acceleration is omega squared times a. So right now, just to sort of summarize, we are looking at a system that can be described as the force being negative some constant times the displacement. From that, we basically get a differential equation. And the differential equation is second derivative of x with respect to time is negative k over m times x. How you solve all differential equations, obviously I'm oversimplifying it, but you guess at the answer, and then you make it work with the conditions you're working for. The general solution to this differential equation, where if I take two derivatives of the position, I end up with my same function times some constant, is sine or cosine. So the most general solution is position as a function of time is a cosine omega t plus phi naught. A is the amplitude, which is the maximum distance from equilibrium. Omega is called the angular frequency. T is just the elapsed time, and phase angle sets our initial conditions. It describes my initial position and my initial velocity. If I take a derivative of position with respect to time, I get an equation for velocity with respect to time. If I take a derivative of velocity with respect to time, I get an equation for acceleration with respect to time. So right now, we haven't actually been specific about this system being a spring connected to a mass. So now what we do is we try and figure out if this is always going to be true, what does my value of omega need to be? So here's the differential equation we're trying to reproduce. And actually, they forgot a little m here. Is the second derivative of position with respect to time is negative k over m times x. Well, here is my x as a function of time. Here's the negative k over m. And here's two derivatives of position with respect to time. Remember, I had this negative a omega squared cosine omega t plus phi. Well, the only way for these two sides to always be equal is if negative a omega squared equals negative k over m times a, or if omega squared equals k over m. So omega is the square root of k over m. So now this is specific to a spring mass system. The solution to the differential equation is position as a function of time is a cosine omega t plus phi naught. And if we're talking about a spring mass system, omega is the square root of k over m. And keep in mind that, well, let me just pause there for a second. Let me just stop for a second. I've been talking a lot here. So, spring connected to a mass undergoes what's called simple harmonic motion. And that's really motion where I can describe position, velocity, and acceleration as a sine or cosine curve. The thing about a restoring force is the farther I get from equilibrium, the more force there is trying to restore equilibrium. Once I have this mass oscillating back and forth on a frictionless surface, I can use equations of, well, I could solve the differential equation to get position, velocity, and acceleration versus time. I didn't really go through the exact derivation of it, but the way you do many differential equations is here's a general form. Let's plug in some particular values to make it work. So the general solution, we chose cosine. Position is a cosine omega t plus phi. And then if I differentiate that once, I get velocity. Differentiate that again, I get acceleration. Let me just pause for 30 seconds, see if there's anything I can explain in more detail before I jump in. Probably spend maybe another 10 minutes talking about simple harmonic motion and then continue with it on tomorrow. Not tomorrow. What is today? Thursday. Continue with it on Monday. Okay. No questions. Let me go back to the screen share and just look at this one more time. So again, let me just velocity, acceleration. Let's reset, make this block a little more massive. Okay, so if I pull this down, let it go. As this thing is oscillating up and down, if I wanted to get the position as a function of time, whatever the equation, can I write on, I can't write on this part. Anyway, the equation describing the position of the function of time is going to be this cosine function. That cosine function has omega in it. The omega that we have in the equation for simple harmonic motion, we call it the angular frequency, but it is related to the omega of circular motion of something moving in a circular path at a constant speed. So that omega in radians per second that this little arrow is rotating at would be the same as the omega that I would use in the equation for simple harmonic motion. If I project, if I look at the y component of this as it's moving in a circular path, that gives me the y component of this mass oscillating up and down. Continuing with that analogy, when an object is moving in circular motion, the velocity is always tangent to the path. And if I look at the y component of this little blue vector as it's moving in a circular path, that will give me the velocity of this mass as it's oscillating up and down. So at the highest point, the object, the mass, is momentarily at rest for a split second. This vector has no y component. And if I continue forward, when it's crossing the equilibrium position on the way down, that's when it has its maximum velocity pointing down. And if I look, this has the greatest negative y component. And then again, once it reaches the other extreme, it's momentarily at rest for a split second. The y component of this is 0. And then again, if I want to know about the acceleration, as something's moving in uniform circular motion, acceleration always points towards the center of the circular path. If I look at the y component of this vector, the acceleration vector, That gives me the acceleration of this block as it oscillates up and down. The acceleration is a maximum when it's compressed, when it's stretched the most. So here it's stretched downwards. So the force is upwards. That's the acceleration. If I continue forward, the equilibrium position is when it's not stretched or compressed. Let me do it on the other side. Here, the y component of the acceleration vector is 0. At the equilibrium position, there's no stretch or compress. I have the acceleration at 0. Okay, let's go back to let me talk about the phase angle. Let me just do a quick little example about the phase angle. Okay, so let's take a quick look at conceptual 15.4, and then I think I'll just sort of call that today for this lecture. So here is a plot of position versus time. I have it starting at t equals 0. So it's going between x equals a and x equals negative a, but at t equals 0, it's at 1/2 the amplitude. So the question here, and we're just going to look at part A, what is the phase constant for this particular setup? And again, the way to think about this is our general equation is position as a function of time is the amplitude times the cosine of omega t plus the phase angle. One thing to keep in mind, if I plug in t equals 0, so x at t equals 0, what I'm going to get is a times the cosine of the phase angle, right? If I plug in t equals 0 here, that term drops out. Well, in this particular case, at t equals 0, it's at 1/2 the amplitude. So what I get is 1/2 a equals a times the cosine of the phase angle. Cosine of the phase angle. So again, I'm plugging in what is the value at t equals 0 of x. When I plug in t equals 0, this omega t term drops out. So what I have is my position at t equals 0 is a times cosine of the phase angle. Well, if I divide both sides by a, what I get is I want the cosine of the phase angle to be 1/2. So my phase angle is the inverse cosine, inverse cosine of 1/2. Now here's one important thing that I don't see a lot of books describe in detail. If you plug this into your calculator, what your calculator is going to give you is the phase angle is pi/3 radians. But the actual answer is plus or minus pi/3, and you need to figure out which one it is. So I don't know if you remember this trigonometry identity, but cosine of theta is the same as the cosine of negative theta. So cosine of pi/3 is the same thing as the cosine of negative pi/3. In both cases, it gives you 1/2. So here's the question. How do you determine whether or not I'm going to use, or how do I determine if I'm going to use pi/3 or negative pi/3? And the answer is you also need to consider the velocity. So remember that velocity is the slope of position versus time. And if I look, I could have x equals 1/2 a. Both of those give me x equals 1/2 a. But in the first case at t equals 0, my slope is positive. So I have a positive velocity. In the other case, my slope is, come on, here the slope is negative. So I have a negative velocity. So what I want is what phase angle is going to give me a positive velocity at t equals 0. Well, one way of looking at it is velocity as a function of time is negative a omega sine omega t plus the phase angle. So my velocity at t equals 0 is negative a omega times the sine of the phase angle. So if I want my initial velocity to be positive, that means I want this sine term to be negative because I'm multiplying by negative a omega, which means my phase angle is going to have to be negative pi over 3. So I'm going to start off on Monday sort of reviewing the phase angle and things like that. Probably only going to spend one more day on simple harmonic motion and then do one day on chapter 16, one day on chapter 17. Couple things. Let me just stop this share. I know that people are busy and my goal is not to have you do a ton of stuff on your own in terms of studying for the final things I didn't cover. So I'll be specific about what I'm covering from chapters 15, 16, and 17. Chapter 15, we're pretty much going to do simple harmonic motion and pendulums. And so I'm going to finish up simple harmonic motion on Monday, talk a little bit about pendulums. Tuesday, chapter 16, I'm going to do in one day, traveling waves. And the one thing I need to make sure I get to is interference, because once you study chapter physics 4C, that's going to come into play. So I'm not collecting homework from chapters 15, 16, and 17. I'll sort of be specific about which ones are good to look at for the quiz that'll be next week. But yeah, we're kind of at the home stretch, and I'm going to just pick and choose the last remaining topics. That said, it's going to be important to sort of read ahead. So if you haven't read chapter 15 yet, please make sure you read it. Focus on simple harmonic motion and pendulums and energy in simple harmonic motion. So you will assign the homework but not collect it. So it's still the exact same homework that I signed before, but I'm not having you upload it through Mastering Physics, and I'm not covering everything. So some of the homework problems will not even be applicable. So I'll tell you specifically like which homework problems will be good to look at when reviewing for the quiz, but the quiz will be sort of somewhat short, straightforward, and just cover the most important things that I covered from each chapter. So I am officially, what am I doing? Taking out lecture, bringing in office hours. Questions I can answer on anything from chapter 12, chapter 15, lab 10, anything like that. I'm going to be around for the next 20 minutes. Is there a Cabrillo class for applied physics in nature? There is not. So yeah, I don't even know of any community colleges that do have a class for applied physics. So yeah, I'm not sure. We definitely don't, and I'm not sure of any other community colleges that do. Thank you, everybody that joined me live. Have a wonderful weekend. Yeah, home stretch. I'm really happy with the way people are doing. Can we look at homework problems 8, B, and 10, or 88 and 10? Let me pull up chapter 12. Did I do more lecture notes? End of chapter. I did. Okay. Homework problems. Let's share the screen. All right, pull this up, chat. Over here, move that over there. Homework chat 12, problems 88 and 10. One, for this one, what is the rotational kinetic energy of the Earth? So we're going to treat the Earth just as a solid sphere, even though it's not completely accurate. So for the rotational kinetic energy of the Earth, which you would use is, it's 1/2 I omega squared. For omega, or for I, you're going to use 2/5 mr squared. And for omega, that is the rate at which the Earth is rotating. You know, it's rotating on its axis once a day. So you could get omega as in omega is just going to be basically 2 pi r divided by the period. In this case, r would be the radius of the Earth. T would be the period, which would be 1 day. But you'd want to have that in terms of omega, sorry, 2 pi r divided by the period. Just 2 pi r divided by the period. I'm sorry. This omega, I was thinking in terms of speed. My omega, I know that I'm moving one circular path, which will be 2 pi radians divided by the period. So period, 1 day, 86,400 seconds. You just need to look up the mass of the Earth and the radius of the Earth. Let me just do 88. Let's see, 88.
I think they were talking about problem 8 and 10 from Mastering Physics, not from the book.
Problem, oh.
Yeah, not the problems 8 and 10 in chapter 12 homework, but if you go to the Mastering Physics, it was 8b and 10.
Okay, so those are homework questions. Let me think, what's the best way to stop this share? Let's pull this up, pull up Mastering Physics, sign in. All right, nights. Come on, assignments, chapter 12 homework. 8, which is problem 1217. All right, so problem 1217. A 25, is it this one? A 25 kilogram door is 220 centimeters tall, 91 centimeters wide. What is the door's moment of inertia for rotation on its hinges about a vertical axis?
Yeah.
Okay, so here's one where you'd be using the
second part of that question.
The second part. So here's one where you're going to be using the parallel axis theorem. So we have an equation for a slab. I forget how they call it, but where the axis is through one end. So you know what the moment of inertia is for rotate. Let me just go to my lecture notes real quick. Do I have those? It must be on this one. Okay, so we have a plane or slab about an edge. So that's how you got the answer to the first part, right? Just 1/3 ma squared.
Mm-hmm.
And then now what we want is an axis which is not through the end, but which is parallel to it. Go back. Oh, did I share this? I think I'm doing this stuff without sharing it with you. Share screen. So yeah, we're using this planar slab about one end. And so for this particular one, now you want it 15 centimeters from one edge. So now you're basically going to have an axis not through the end, but an axis here. So this distance is going to be my 15 centimeters. What is the door's moment? Solid door, that tall, that wide. What is the door's moment of inertia? So this is when you're going to use my moment of inertia, this parallel axis theorem. I plus m d squared. But just so you know, I'm not going to test you on this. So this is one of those ones where I didn't quite cover it in enough detail to go through everything. Let me just quickly look at this other one. Problem 10 from Mastering Physics.
It's 1260, so it should be number 16.
1260, perfect. All right, share
Yeah.
the screen. 1260. Oh, this one?
Let's see.
That's it.
So yeah, you know, I wouldn't worry about that one. I could go through it with you, but it's like a 20-minute problem, and it's way more in depth than I would be covering for the celebration or for the quiz. So if you want to, I can go through it with you,
So-
but it's not.
Okay, as far as like leaving it off the homework, it's okay to just not.
Yeah, we're being scored on it.
Yeah, I mean, just so you know, the scores that you get from mastering physics, as long as you try most of the problems, I'm pretty much giving everyone who attempts it 10 out of 10, unless they only try a couple problems. So don't worry too much about the
Okay.
exact answers for every single one. And I had like probably 4 or 5 people email me yesterday being like, oh my God, this homework is so hard, I can't do it. And yeah, I apologize for just not being able to cover everything in the amount of detail, but I didn't want to change the homeworks because this is still the level that, in an ideal world you should be able to do, but this is not an ideal world at the moment. Haven't taken the quiz yet. How does it compare to the homework? Chapter 12 is still due, but again, yeah, if there's a super challenging problem, you can request the answer. Again, the homework solutions are still posted, but don't kill yourself on some of the harder homework problems. You'll see that the quiz, like I talked about, is relatively straightforward. I think I missed somebody. Can you run through homework 1260? Yeah, because that answer didn't include. So just real quickly touching on just this one, if you want to go through the conceptual stuff. 40 kilogram, 5 meter long beam is supported by, but not attached to, 2 posts in the figure below. 20 kilogram boy starts walking along the beam. How close can he get to the right end of the beam without falling over? Okay, easiest way without me trying to do all this, let me see if I can share. Let's see if the homework solutions are in enough detail to share them. Homework solutions, chapter, no. Yeah, homework solutions, chapter 12. 1260. Okay, so yeah, so this is one I definitely didn't cover in enough detail. Now I just lost this. Share screen, homework solutions. So here, if the center of mass of an object is not moving, can I write on this? I can't write on this. If the center of mass of an object is not moving, then I know the sum of the forces on the object has to be 0. If the whole thing is not rotating, then I know the sum of the torques has to be 0. So I can't really draw on this, but if I look, if I have an extended object and I want to look at something about the energy of the object or the force of gravity on it, I always am looking at the center of mass of the object. So for a board that's uniform density, the center of mass would be right smack in the middle. So if I'm looking at, let's say, the sum of the forces on this, if it's at rest, the sum of the forces has to be 0. I have 3 forces acting on the board, 4 forces acting on the board. I've got the gravity, force of gravity on the board pulling it down. I've got the person's weight pushing down. And then I have you could call this the normal force of each one of these supports pushing up. So I have one equation that says the sum of the forces has to be 0. But since this is not rotating, I can also say the sum of the torques has to be 0. And one of the cool things about it is I could look at the sum of the torques about any axis. Meaning, I could place my axis here and say the sum of the torques about this point. Can I stop? How do I just more breakout rooms? Yeah, there's no easy way for me to draw on this. I could look at the sum of the torques about this axis and so on. So what you're doing for this problem is you're looking at the sum of the forces equals 0, and you're also looking at the sum of the torques equals 0. Conceptually, it's not too bad, but mathematically, well, this is something, again, that I just didn't quite have time to cover. But for something like this, you will, if you're an engineer, have an entire course statics. That's literally all sum of the forces equals 0, sum of the torques equals 0. So if I know an object's at rest and not accelerating, I know the sum of the forces on it have to be 0. And if it's not rotating, I also know the sum of the torques on it has to be 0 also. And that's all this problem is sort of getting at from a conceptual point of view. Other questions I can answer on that, or anything from chapter 12, 15, lab 10?
I have a question for lab 10. I just wanted to kind of run through my lab with you really quick. Well, just like ask you about it.
Okay, sounds good.
I think I'm just gonna try and figure out the first one, the rubber band one.
Okay.
So in order to do that, actually, hold on, maybe I will show you. I was thinking I have my water bottle,
Mhm.
and I have rubber bands, and I was thinking I could measure the weight with the water, because like the density of water, turn it into.
As one way I was going to suggest people could get masses if they wanted to is, we know the density of water, most people have measuring cups, something like that. So you could get the mass of a known amount of water.
Okay, cool. And then I was gonna like hang it from my little bar over there, and
Right.
then.
So for that, what you're going to want to do is, one, you need to somehow calibrate the rubber band. So you need to have a bunch of things sort of a known mass that you can hang off the rubber band so you can get the spring constant. And once you have the spring constant of the rubber band, then you can hang an unknown mass from it. And from how much it stretches, you could figure out what the weight of that object is. So what you'd want to do is somehow calibrate the rubber bands so you know about what the spring constant is, and then measure a known amount of water so you know what the mass should be. And then you can hang that from the rubber band and see if the mass you get from the rubber band stretching corresponds to the mass of water you know should be there.
Okay, so I have to use something other than water to calibrate the rubber bands.
You know what? You could use water to calibrate it. Like, what I want people to do is not just calibrate it, but then ideally try and use that to measure the mass of an unknown object. So like somebody else is doing something similar where they have an old cell phone and they went on the internet and found out what the mass of that cell phone is. And so they're going to try and get the mass by using rubber bands and then compare that to the mass they got by looking it up on the internet.
Okay, so first I'm going to calibrate it with water, and then I have to try and guess the mass. No, wait. Then I'm going to use my rubber band to calculate the mass of an unknown object. But I actually know I have to compare it to it.
Right.
I actually have to know the mass.
Right. And
Okay.
one thing to keep in mind too is you also have the mass of the water bottle itself. So what I would do is maybe hang the water bottle by itself, see how much it stretches the spring, and then look at how much additional stretch you get every time you add, more water to it.
Yeah.
Yeah, that should be totally doable. And just so you know, we've never done this before. I don't know if rubber bands really do obey Hooke's law over a wide range of stretches. So I would say start on it, not at the last minute, because you may run into some challenges. And it could just be, does a rubber band obey Hooke's law? If it does, then you can use it to get the mass of an unknown object like a cell phone or something where you could look up the mass.
Okay.
If it doesn't, then maybe you could develop some equations that, well, it didn't quite be linear, but yeah, do the best you can.
Jordan
Okay.
and I did something with rubber bands, and they're weird.
They are weird. So my guess is they don't obey Hooke's law. Or if they do, it's only over a sort of narrow range of how much the rubber band stretches.
Okay. Cool. And then I was wondering also in that sort of area, I was thinking like I have a bunch that are similar rubber bands, and maybe doing like one and then adding another one and like seeing if the two are proportional to each other or something like that, like if their K changes.
Yeah, no, I'm totally get creative. You don't have to do exactly what we said, but yeah, you've got rubber bands, you've got water that you can get the mass of. So come up with something that's exciting to you and you feel like you can get some kind of meaningful result out of.
Okay, thank you.
You're welcome.
And then wait for the presentation on
Yeah.
Wednesday, because I would much rather do a presentation than a lab report.
So the presentation would be sort of along the same lines of a formal report. So I'd want a little introduction of what concepts you're testing out, procedure, exactly how you did the experiment, some way of presenting your data, you know, write it on a board or something, show me how you did the analysis, and then just a conclusion. You know, so I was trying to see whether or not rubber bands obeyed Hooke's law. Here's how I did it. Here's the setup. Here's the data I took. Here's what the data showed, and it either does or doesn't obey Hooke's law. So figure, you know, 5 to 10 minutes, but the same kind of information that you would have in a formal report.
Okay, and the presentations are next Wednesday?
Next Wednesday.
At what time?
It'll be the normal time. I'll probably add another hour, so I'll probably be available online for like 3 hours. And then if for any reason you can't make one of those, you could just film yourself doing the presentation and then just send it to me.
Okay, so it'll be our normal lab times, just
Normal lab times, and then I'll probably throw in 1 more hour just to, yeah, give people some options.
Okay.
Sound good?
Thank you.
You're welcome. Marco, do you got a question?
Yeah, I was wondering if you'd gotten my email on my lab.
You know, I did, but I didn't get a chance to look at it. So, yeah, you had it. Yeah, I didn't look at it at all.
Okay, yeah. So like pretty much I tried to make like a little iMovie, like filming like the process of like making my lab, and then like I showed all the videos, and then like I also sent like a separate Excel sheet like
Okay.
about values and stuff. And I was just wondering like what else I would need to include for that.
I haven't watched the video yet, but I mean, if you gave me your data so I can clearly see it, and if you did a little video presentation on what you're doing, what the procedure was, here's your data, that's pretty much what I'm looking for.
Okay, yeah, because I'm happy to like just send you that, but then also like just do the presentation as well to cover whatever I missed.
I'll look at it at some point this weekend, and then I'll get back to you either way and just let you know this is fine as is, or I'd like you to do a 2-minute just presentation on this stuff in particular.
Sounds great. Okay, thank you so much.
All right, take care, Marco.
All right, you too. Bye.
Any other questions from people online? Leo, you got a question?
Yes. Can you go back to the notes and explain a little more on differential equations?
I can. In fact, let me just do it on the whiteboard, so I'm not just repeating it. So our general system is really just a mass connected to a spring. And I know the force the spring exerts, which is negative kx. And I know from Newton's second law, the sum of the forces equals ma. So my general equation, sort of for a mass oscillating back and forth on a spring, is mass times acceleration equals negative kx. And I know acceleration is the second derivative of position with respect to time.
Oh, okay.
So what I have is mass times the second derivative of position with respect to time equals negative k times the position, or the second derivative of position with respect to time is negative k over m times the position. This is a second order differential equation, which if you haven't had it yet, it doesn't really matter. It's just an equation that's got, you know, derivative of position with respect to time. In this case, the second derivative position with respect to time. And the way the differential equations, many of them work, is you've got this general form of an equation that has what's called a general solution. And the general solution is something that when I take 2 derivatives of it, returns the original function plus some constant, which is negative. And sine and cosine are the sort of classic examples. So you could choose to use either sine or cosine. Most books use cosine. And so the general solution is a times the cosine of omega t plus some phase angle. So a is just the amplitude. This is just the maximum that you can be from your equilibrium position. Again, keep in mind, right, cosine is just varying between 1 and negative 1, which means my position's going from x equals a to x equals negative a. Omega is called the angular frequency. T is just the elapsed time, and this is our phase constant. So this is just a general solution to anything really where I'm taking 2 derivatives and returning the original function. Now what I want is, how am I going to relate that to my particular system? Well, I want it so that when I take two derivatives of it, I get negative k over m times x. Well, if I take two derivatives of, so if I take one derivative of x, dx, oops, eraser. Let's go back to draw. Here's my position versus time. I take one derivative of this, dx dt. Derivative of cosine is negative sine, but I also have to take the derivative of the inside, which pulls out an omega. So I get negative a omega times the sine of omega t plus phi. And then if I take a second derivative of sine is cosine, but again, I pull out another omega, I get negative a omega squared cosine of omega t plus phi. Well, I want this equation to be true in all cases for an object oscillating back and forth in simple harmonic motion connected to a spring, which means I want the second derivative of position with respect to time to equal negative k over m times position with respect to time. Well, my second derivative is negative a omega squared cosine omega t plus phi. And if I want that to equal negative k over m times my position, which is a cosine omega t plus phi, the only way, if this is always going to be true, is if omega squared equals k over m. And so omega in this term for simple harmonic motion with a mass connected to a spring is given by the square root of k over m. For a pendulum, there's a different equation for omega, but in general, anything oscillating back and forth, you can describe with this equation. Position is a, the amplitude, times cosine omega t plus phi, and omega is going to depend upon what kind of system you have. For a pendulum swinging back and forth, it's only going to depend upon the length of the pendulum and the acceleration due to gravity. For a mass connected to a spring oscillating back and forth, it's only going to depend upon the spring constant and the mass.
Okay.
Okay, I have to go. I have like if anybody has a quick little 30-second question, I can answer that. Nope. All right. Have a wonderful weekend. Thank you for everybody who joined live. I will see you on Monday.